Hopefully you've had a chance to work this Gibbs free energy test yourself kind of thing, right? So this is an old quiz I had given at one point, but I just figured it was nice to work some of those problems since we're not getting to work problems together in class. Give you a chance to work a few, or you can just kind of work them along with me here as I go. See if you can stay a step ahead of me kind of thing. So first question, the enthalpy vaporization for methanol is this. At the boiling point of this, calculate the entropy change for methanol going from liquid to vapor. Well, I know it's going to be positive, right? Because we're going from liquid to vapor. So we're going to have a positive delta S. When they say enthalpy of vaporization, maybe I'm starting to get worked up about all that stuff, what that means, but that's basically delta H for this process. And I know what temperature it's at. So when you say, well, we've got delta H, delta S, but they're not talking about surroundings at all. So I'm thinking, well, maybe this has to do with delta G equals delta H minus T delta S. And we say, well, how could we know? Well, they don't say anything about delta G, but they do say the heat of vaporization at the boiling point of this. Well, when you're at the boiling point, is it spontaneous to boil? Is it spontaneous to go back from boiling, to condense? So it's spontaneous to both those things. It's right at zero, right? It's right at equilibrium. So because of the words in this problem, and that's probably the toughest part of this one, is I know delta G is zero. It is not spontaneous for water to boil at 100 degrees Celsius or to condense. It is spontaneous for both of those. It's at equilibrium right there, right? Same thing with water freezing and water melting at zero. If you're ice and you get to 0 degrees Celsius, you're not going to instantly start melting. You've got to start adding a little bit more energy. You're right at equilibrium there, right? You're not going to see a change. So since I know my delta G is 0, then I have delta H, 0 is delta G. So delta H is 35.3 kilojoules per mole minus the temperature. So 64.2 in Kelvin, 64.2 plus 273. Since they are giving me 0.2, I'll go ahead and put the 0.15 in there. Minus the temperature, which is 337.4 Kelvin times my delta S, which is what we're looking for, right? So all I have to do is 35.3 divided by 337.4, and that's going to give me a delta S of 0.104, well, I guess 105 actually, 105 kilojoules per mole Kelvin, or 105 joules per mole Kelvin is how we normally do those, right? So the key idea on this one is if you're at an equilibrium state, if you're at a boiling point, if you're at a freezing point, anything like that, then you know your delta G is equal to 0, so then you can relate it that way, right? It's probably one of the more challenging ones on this little test yourself quiz. Calculate the standard entropy change for the following reaction. So we want the entropy change, so delta S, and then they give me some of these. So this is just a products minus reactants sort of thing. So it's going to be delta S of the products minus delta S of the reactants. I only see one thing that I'm concerned about, and that's I'm going to have to multiply the oxygen by 1/2, right? Other than that, it's just products minus reactants. So 42.63 joules per mole Kelvin minus 205.14 over 2 joules per mole Kelvin. I don't really have room for, that's some ugly units there. You can't even read that. Plus 33.15 joules per mole Kelvin. So 42.63 minus 205.14 divided by 2. And minus 33.15. So that is a negative 93.09. We have 4 sig figs everywhere. Yeah, it looks like we've got 4 sig figs everywhere, so there's no reason to drop any of those. Joules per mole Kelvin, right, is our delta S. All we have to do is products minus reactants. If you have coefficients, remember amounts matter on this kind of stuff. So if we had a 2 or a 10 or whatever, right, we had a half, so we multiply by half. Given the following information, calculate delta G for the following reaction at 298 K. Is it spontaneous? So they want to know, is it a positive delta G or a negative delta G? Let's go ahead and slide this up here so we can see it a little better. They gave us, let's see, what did they give us? They gave us S's and H's for these things. So this one's going to be a little more involved, right? We're going to have to figure out what the delta S for the reaction is. We're going to figure out what delta H for the reaction is. And then we'll do delta H minus T delta S. So delta S of the reaction is just going to be the product, which delta S is 186.69 times 2 minus, that's my products, minus my reactants. And my S's for my reactants are 130.58 and 222. We want to get the whole thing there, right? So use your parentheses correctly. 222.96. That's going to be my delta S for the reaction. Delta H products are negative 92.3 notice this is a kilojoules and a joules thing again, per mole for the products, minus, they didn't give me any for the reactants. Oh no, I'm sunk. I'm not looking anything up or anything, right? Those are both elements. Enthalpies for elements are 0, right? So I can just ignore those guys, right? So just doing some calculations. When we do our calculations, we get a 19.84 joules per mole Kelvin. I did forget to say, since there are 2 of those, I do need to double that one, just like I doubled the 186 joules. So that's a negative 184 there. So when we go to do our delta G reaction, it's going to be negative 184.6 kilojoules per mole Kelvin. Minus the temperature. What did they say? The temperature was at 298 Kelvin. Times 0.01984 kilojoules per mole Kelvin, right? We got to get our units to match there, so make sure we get that into kilojoules. So we go negative 184 minus 298 times 0.01984. And that's going to give us negative 190 kilojoules per mole Kelvin. So that's our delta G. And then they said, is it spontaneous? Yes, it is spontaneous. It has a negative delta G, so it is spontaneous. In fact, it's exothermic and becoming more disordered. So barely, but it is becoming more disordered. So this would be spontaneous all the time, right? At all temperatures. Doesn't mean it would happen quickly, but it doesn't mean it would be spontaneous, right? So we look at the last couple here. Number 4, predict. Get that in focus a little bit. Predict the sign of delta S of the surroundings for each of the following changes. So remember, delta S of the surroundings has to do with how much heat is involved. So if we are becoming more disordered, then you're going to have to kick heat into it. That's going to be an endothermic process kind of thing. So that's going to make the surroundings less disordered and that kind of stuff, right? So it's delta S of surroundings. So let's go through these guys. Water liquid going to water gas. Well, I'm going to have to kick heat into this. This is endothermic. And we do have our delta H equals delta S of the surroundings divided by T. Nope, I flipped that around. It is delta S of the surroundings equals delta H divided by T. Yeah, I said that backwards the first time. Sorry. The negative of the delta H, right? They're opposite signs and that kind of thing. So I don't really like going through the equation. I like thinking it through, right? But so this is an endothermic process. So you're having to put heat into it. That means you're going to make your outside, it's endothermic. So heat is going in. That's going to mean the surroundings are less disordered. The surroundings are going to have to give some heat energy. They're not going to change what the chemicals are. They're just going to move a little less. So the delta S of the surroundings for this first one would be negative. Delta S of the surroundings, because they have to give some of their energy to the water to make the water boil or to make the water evaporate. Here you're going from gas to solid, so it's depositing. So if it is depositing, it's going to give some energy out. That's going to be an exothermic process. Since this is an exothermic process, that's going to heat up the surroundings a little bit. If that heats up the surroundings a little bit, then that's going to be a positive delta S of the surroundings. because as we heat up those surroundings, they're going to become more disordered. The higher your positive value, the more disordered you are, right? So just go with that. Endothermic, exothermic, the surroundings are really based on the heat for that kind of stuff. So then we see number 5. This is a good old Hess's law, but with delta G stuffs. So we see these, and I see a series of reactions, and I know I need my overall reaction to add up to this guy here, right? So when I see this, I start looking for the things that aren't in a bunch of places. So like my methane is right here. So I'm going to flip this first one. When I flip this first one, CH4 goes to C plus 2 H2s. My delta G is now going to be a positive 51. We flip the sign on delta G when we do that. We see the next one. There's not a lot unique in that one. Well, the water's unique in that one, I guess. And I see a water here, but there's no other waters. So I'm going to put this one in half. So H2 plus half an O2 is going to go to H2O. So that means I'm going to need to cut that 474 in half. So my delta G is going to be negative 237, right? Because that's my only water. So if there's only one here, then I know I have to have half of this one. I can't cancel that water out anywhere. So then I see what is left with stuff, and I want to get rid of this carbon. I want CO2 on the product side. And so on. Oh, we're going to have to edit this video. Well, now I'm going to be lazier than that. I typed this wrong, didn't I? I typed this wrong. There should be a 2 there. That's not balanced right. So we're not going to cut this in half. That should be a negative 474 right there because we do need 2 there, right? Or the other things won't balance out. But when I do that, I've got 2 hydrogens on the product side. I've got a carbon on the product side. I see a carbon on the reactant side, and I need 1 CO2 on the side. So I'm going to leave this last one alone also. So really, it's just the front one that we're having to flip there because my H2s are going to cancel out. It's 2 H2s there because I did not cut this one in half. My H2s are going to cancel out. My carbons are going to cancel out. So I have CH4 plus 2 O2s is going to make CO2 and 2 H2Os. And this last one didn't change. So that delta G is negative 394. So we're going to go 474 plus 394. That whole thing's a negative. And then, so it is going to be a negative 817 kilojoules per mole for this whole reaction. All right, hopefully this is helpful. Come see me in the Google Meet if we're struggling with how to do these or how we know what equations to use and that kind of stuff.